Welcome back. Let's solve two example problems on how to solve input impedance in circuits when they're given to us in DC analysis form. Here we have two examples. We're going to start with example one. Let's zoom in here. When we focus on this problem, the first thing we see is that we have a NPN. This NPN means that we're going to be focusing on the base and the emitter of this circuit. And the first thing we do when we're going to focus on these problems is we want to convert them to AC analysis. How do we do that? The first step is going to be to ground. I'm going to just write it like this: ground anything that touches VCC. The second thing we're going to do is we're going to short any capacitor. Capacitors in the circuits sometimes look scary, but in terms of AC analysis, they typically actually almost always help us. So let's start doing this, or let's make the circuit an AC analysis. Let's start by duplicating the circuit. I'm gonna move it down here. And I'm gonna move these two steps we have to do down here too. Okay, let's get started. Let's start with the first step. Let's ground VCC. We're gonna do this by simply getting rid of it, and we're gonna ground anything that touches it. This includes RB and RC. The second step is to short capacitors. I'm gonna short capacitors with this pink line right here, this pink wire, and I'm gonna delete the capacitance. Everything's looking good. Let's now, sorry about that. Let's redraw the circuit by moving resistors around in ways that look more appropriate and more helpful to us. Let's start with this RC. I'm just gonna move it down here. Let me move it a little more to the side by moving this V out. Connect it right here. Our RC is right here, and this resistance is still connected right there. RB is connected to the node below it. Let's move RB down to. We'll move it down here. Nothing at this point after we showed the capacitors, nothing I've done has changed this circuit conceptually. Rather, we just move the resistors down without changing the circuit at all. So the second thing we need to know is where this input signal is. This input signal is going to imply a current in this direction. And this current is going to go through the emitter, and it's going to come out from the base. Okay. The next step is to look at where we're supposed to find our input impedance, right here where this Rn is at. Let's make a node right above it, right here. What this means is that as we start going through the circuit in the current direction, direction of En, we keep going until we hit that node. And everything before that node is going to be completely ignored in our input impedance formula. So we're going to have Rn, and we're going to ignore everything in pink that's highlighted in pink. And as we keep going, I'm going to start with this green highlight. We notice that we hit the emitter arrow. Remember, this emitter arrow has a resistance of R pi. Let me move this arrow right here. This emitter arrow has a resistance of R pi. And as we continue going after R pi, we realize we reach this point. And we need to also understand that we're going to completely ignore RB because it got shorted out by this capacitor. So we could completely neglect it. This gets to another point. We have R pi, like I mentioned. We hit R pi first. Everything that's in pink right here would not have to be multiplied by a constant. Why? Because everything right here would be in series or directly in series or directly in parallel with this voltage source right here. After this point, after we pass the emitter, this whole green section that's highlighted in green right here is going to be multiplied by a constant because it is now the base. And this constant, since we're starting, or since we have our voltage input signal in the emitter, this input signal is going to be, this constant is going to be 1 over 1 plus beta. And this is going to determine our entire input impedance for this circuit. This is really easy. This shouldn't be so confusing, as RB is completely ignored, and that's the only special case about this circuit. Let's move to problem 2. And problem 2 could look a little insane at the start. Let's pay attention to it. We have a NPN, and this NPN is going to mean that we have our emitter right here, and that our base, and we're going to have our base right here. And those two legs are what we're going to focus on primarily. The second thing is that we have our input signal, Vs, down here. And this input signal is going to implicate a current direction, but it also means that we're not going to multiply anything in the base by a constant because it is directly in series or proportional, directly in series or parallel to this Vs. Everything after it, after R pi, would be multiplied by a constant of 1 plus beta. So let's get started by first making this an AC analysis. Let me duplicate this circuit. Move it down here. Hopefully we could see our steps. We're gonna ground VCC and then short capacitors. So let's first ground VCC. We're grounding VCC at RC and at RB. The second step is we're gonna ground, or we're gonna short every capacitor. Let's short capacitors. All right, now we could get rid of them. Perfect. We're basically done. I like to move resistances a lot around so that they are easier for us to understand. I'm gonna move this RC down here. This doesn't change anything. Remember that. And I'm gonna move this RB1. I'm gonna move this RB1. Right here. Perfect. We're ready to get started. So we are being asked to find our input impedance after this point. This point is going to be right here where Vn is. So let's start looking at our current. As we start following the implied current of Vs, we reach Vn. And everything at this pink highlight is going to be neglected or ignored in our input impedance. So let's go afterwards. Let's keep moving on. We split, once the current keeps going, we split at RB2, and we keep going till we reach RB1. Let's stop right here. What do we notice about these two resistors? These two resistors, they're in parallel. They're in parallel. So I'm going to write their resistance as some other resistor, RZ. RZ is going to be equal to RB1 in parallel to RB2. Okay, perfect. Now, this resistance in green is RZ. The second thing we need to realize is that this RZ is going to be in parallel to the entire circuit after that point. It's going to be in parallel to this entire part. So RZ over here to the right is in parallel with this half of the circuit. Okay, let's get rid of that highlight. let's go through the circuit one by one. As we get to this part of the circuit, we hit our pi. We cannot forget our pi. We have our pi. As we pass this part of the circuit, we hit RE1. Now remember, our input signal is at the base, which means everything in the emitter after this emitter arrow is going to be multiplied by a constant of 1 plus beta. So let's do that. 1 plus beta. So after that resistance, you might feel tempted to go through it and go to RE2. Let's pay close attention. RE2 is going to be completely shorted out by the short that was caused by our capacitor, which means we could completely ignore this part of the circuit. And that means, I don't know what happened. And that means we are done finding our input impedance. So hopefully this helped. Please notice that RZ is just the resistance here in the green, and this resistance is completely in parallel with everything in the emitter leg. And that determines our entire input impedance. Thank you for watching. Hopefully these two problems were helpful.